All right, so as we continue with our gathering our data through various methods that we learned yesterday, whether it was stratified or cluster or just a generic simple random sample, that's we want to make sure we focus along those type of things to keep our information from being tainted, being in a way leading to some bias in what's taking place there. As we go through today, we'll talk about observational studies. We'll actually set up the design of an experiment in today's process. Observational studies do not seek to influence or affect results of a study, whereas experiments impose a treatment upon individuals to determine if the treatment may cause some effect. Therefore, to establish a cause and effect, an experiment is the only source of convincing data. In a statistical study, there are variables. We have, of course, your response variable and your explanatory variable, and also like your lurking variables. A response variable measures the outcome of a study. The explanatory variable may help explain or influence the change in response variable. Again, we had those two things in our previous chapter of chapter 3 when we were doing our linear regression. A lurking variable is a variable that is not among the explanatory or response variables in a study, but that may influence the response variable. Lurking variables make it hard to see the relationship between the explanatory and response variables. Since observational studies do not influence what is happening in the study, there can be lurking variables that can mask a true cause and effect. Experiments, however, can by design isolate variables so lurking variables are minimized. What is confounding? Confounding occurs when a lurking variable and an explanatory variable are associated in such a way that their effects on the response variable cannot be distinguished from each other. Whether analyzing a study for confounding variables, be sure to explain how it's associated to the explanatory variable and how it could affect the response variable. Again, as I shared with you all in a previous class about like my wife with gathering data for one of her spreadsheets for the clinics that she's in charge of. She wanted to figure out, well, how many clients were checking in online or whatever, coming into the clinic, but never going back to be seen by a medical provider. They just turned around and left. And she's trying to figure out, well, what is that number? And what, and then she found the numbers for her region. And then it was like, okay, she knows what numbers for each store. And now she wants to see, okay, is there a lurking variable? Is it a certain employee that's causing this to happen at that clinic frequently? And so she's trying to isolate those kind of lurking variables as she's analyzing the data so that they can try to fix a situation, of getting people to come back in, and staying to be seen. So here's our first example. Does eating dinner with their family members improve academic performance? According to the ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades at school. This finding was based on a sample survey at Columbia University. So first off, they asked, was this an observational study or an experiment, and why? So what do you all think? Observational study or an experiment? All right, observational, and why? They didn't impose a treatment, did they? No, they just so they didn't assign people to go certain days a week and so forth. They just, this was a survey. No treatments were involved. Okay. What are the explanatory and response variables? So what's the explanatory and what is the response? So what do you guys think? What's the explanatory? Yeah, eating dinner with their families. Eating with family 5 days per week. Therefore, my response would be, the grades. Does being home, eating with family 5 days a week, does that improve your grades? Is what the survey was. Explain why this study cannot establish a cause and effect. Suggest a lurking variable that may be confounded. We can't do a cause and effect because it's a what? It's not experiment. So, we can't do cause and effect because this is an observational study. And then now, lurking variable. All they said was that they were home eating dinner 5 times a week, at least 5 times a week. Now, if you're eating dinner at home we're assuming with family members, parents are involved. What are parents typically going to do at the dinner table? Discuss your grades. Yeah, so one of the lurking variables is parent involvement. It's the topic of the conversation at the dinner table. And so right now they just said in the survey that they ate at home at least 5 times a week. There are some things that contribute to that. It's parent involvement. Hey, are you going to class? Are you doing your homework? When's your next test coming up? And so that's the lurking variable that may be confounding the results. That the kids that eat at dinner at home at least 5 times a week get better grades. Well, it's because there's probably something influencing it. And again, when you think of that aspect, parents involved, asking about it, checking up on them. If you say something, hey, things are going good, then what's a response for what some parents may do? They may offer some help with where you're struggling. Maybe they say, hey, do we need to get you a tutor? Okay, so now we get some other influences in there of the economic status. Can you afford extra help to get you a better grade, to help you do better in the class? Experiments. When we look at the language of experiments, a specific condition applied to the individual in the experiment is called a treatment. If an experiment has several explanatory variables, a treatment is a combination of specific values of these variables. The terminology experimental units are the smallest collections of individuals to which treatments are applied. When the individuals are human beings, they are often called subjects. So in this next problem, it kind of spans over two on the top page and the bottom here. A study published in New England Journal of Medicine in March of 2010 compared 2 medicines to treat head lice, an oral medication called ivermectin and a topical lotion called methylene. Researchers studied 812 people in 376 households in 7 areas around the world. Of the 185 households randomly assigned to ivermectin, 171 were free from head lice after 2 weeks, compared to 151 of the 191 households randomly assigned to the methylene. They asked us to identify the experimental units, the explanatory variables, what's the response variables, and then what are the treatments. So again, if you want to work ahead of me, you can. As we look at our experimental units, would be our households. What was the explanatory variable? That would be the medicines. What were we trying to, what was our outcome? What were we trying to see for a response? The head lice, free from head lice after 2 weeks. Who had a greater rate free from head lice after 2 weeks. And then our treatments, they were put into one of two groups. One group got the ivermectin. And then the other group got the methalion. Anybody remember what ivermectin was also used to treat? Anybody heard what it was also used to treat, out of curiosity? Some doctors prescribed that to treat COVID when COVID first came out. That was what it was used. So, just a little tidbit. Whether it was effective or not, no clue. I haven't seen the studies. But I knew my neighbor who's a doctor, and then my neighbors across the street from me is their patients, and I was talking with them, and they said that they prescribed that, and felt it did good for when they had the COVID or so forth. So next one, same process, different situation. We got to identify the experimental units, explanatory variables, response variables, and the treatments. Growing tomatoes. Does adding fertilizer affect the productivity of tomato plants? How about the amount of water given to the plants? To answer these questions, a gardener plants 24 similar tomato plants in identical pots in his greenhouse. And then he will add fertilizer to the soil to half of the pots. Also, he will water 8 of the plants with either a half gallon of water per day, 8 plants with a gallon of water, and then the remaining 8 plants will get a gallon and a half. At the end of 3 months, he will record the total weight of the tomatoes produced for each plant. So this one, what are my experimental units? That would be the tomato plants. My explanatory variables, that would be the fertilizer and the water. What did they gauge at the very end? After 3 months, they'll record the weight. So the weight of the tomato plants. And then the treatments. Now this gets pretty detailed for the treatments, because notice not all of them got fertilizer. He said half of them would get fertilizer added to the soil. And then he broke it down even further. Of 8 plants would get a half gallon of water, 8 plants will get 1 gallon of water, and so forth. So with that in mind, we would say that we'd have basically, we have a fertilizer treatment and no fertilizer treatment. And underneath each one of those, we'd have basically fertilizer, and they were given a half gallon of water, given a gallon of water, and given 1.5 gallons of water. And then we would have, on the non-fertilizer, we would have plants that got no fertilizer and a half gallon of water. A gallon of water, no fertilizer, and a gallon and a half. So based on that, I'm thinking we're doing 4 in each group. If there's 24 total, 12 are going to fertilizer, 12 are going to non-fertilizer, and then in those subgroup breakdowns, it's going to be 4 in each group. 4 will get fertilizer in a half gallon of water, 4 will get in the gallon of water with fertilizer, and so forth. And so here we have a little bit more of a detailed set of treatments. But we need to make sure we include both, because you're put into, in a way, a control group and the experiment group where we're adding that treatment of the fertilizer. But we also had the extra treatments with the amount of water they were given. Bad experiments won't take into consideration lurking variables and minimize them. Okay, so as you create an experiment, there's a lot of thought process involved on how we can eliminate lurking variables that way, or minimize it so where it doesn't have that great of an impact on our study of what we found for our experiment, where we're trying to do some cause and effect relationship. Here's an example. Does caffeine affect pulse rate? Many students regularly consume caffeine to help them stay alert. Thus, it seems plausible that taking caffeine might increase an individual's pulse rate. Is this true? One way to investigate this is to have volunteers measure their pulse rate, drink some cola with caffeine, measure their pulse rates again after 10 minutes, and calculate the increase in pulse rate. Unfortunately, even if every student pulse rate went up, we couldn't attribute the increase to caffeine. Perhaps the excitement of being in an experiment made the pulse rate increase. Perhaps it was the sugar in the cola and not the caffeine. Perhaps their teacher told them a funny joke during the 10 minutes period and it made everyone laugh. In other words, there are many lurking variables that are potentially confounded with the caffeine. To minimize lurking variables, we try to make sure groups receiving. Okay. Come on, guys. Oh, I appreciate it. Yeah, makes it easier on their eyeballs with these iPads and stuff doing things. So.
We're here to get filtered.
No worries. Yeah, sure. So to minimize the lurking variables, we try to make sure groups receiving treatments are similar as possible. So the only systematic difference is the treatment. This allows us to be more confident that the results are caused by the treatment. In good experiments, we randomize the comparative experiments, the principles of our experimental design. A proper comparative design ensures that influences others than experimental treatments operate equally on all groups. This helps with the effect of lurking variables. One group should serve as a control group, which provides a baseline for comparing the effects of the other treatments. An inactive treatment gives a control group what is called a placebo. Not all control groups receive inactive treatments. In random assignment helps balance out the effects of the lurking variables that we can't control or don't think of on the treatment groups. That is, random assignment forms groups of experimental units that should be similar in all aspects. So that's like doing our little stratified sample yesterday of like, if you're doing an experiment, maybe it's grouping a strata of all males and then another group of all females. And then now you can also do some subgroup breakdowns of what range of ages are in your experiments. As you're testing certain drugs, and maybe you need to break it down to similar age ranges. As you're doing things. Methods that to create a simple random sample can be used to randomly assign experimental units to treatments. Remember that it is extremely important to describe how many you are randomly assigning experiment units to the treatments, or how you are. So you're going to specify, hey, am I using the hat method with the slips of paper? Are we using assigning everybody a number and using the table of numbers, or are we using a random number generator to grab the sample that people to assign them to? The replication aspect. Use enough experimental units in each group that are so that any differences in the effects of the treatments can be distinguished from the chance difference between the groups. So in that aspect is we want to try to make sure that we have a good size. We're not just putting one person, in there. We need to make sure we have a good size of experimental units. Now, what could go wrong with experiments? We got the placebo effect, a response to an inactive treatment. We can avoid by using a blind study. Sometimes when people know that they're going to be part of a study and they're receiving a treatment, a pill, or let's call it, whether the pill has the true medicine or if it's a sugar pill, a placebo, sometimes that just knowing you're about to get something like, that causes people to think that, hey, it affected them, that helped them. So what we could do is we could do what's called a blind study. You have two types, a single blind and a double blind. A single blind study, the subjects don't know which treatment they're receiving. So as we assign, we by whatever simple random sample method we're doing, they don't know which group they're going to. We don't say, hey, you're going into the control group. You're going into the one that's receiving this. All they know, they're going into Group A and Group B. And they don't know the definition of what Group A and Group B are. A double-blind study, the subjects and the people interacting with the subjects don't know which treatment they are receiving. A double-blind would be the perfect way because sometimes if you're trying to get information or data to support your case on why people need to be taking something or doing something, you can try to rig it to where you have certain people in that true treatment, the actual pill or whatever, and that will in turn, try to give you extra information. Hey, this is why we need to mass produce this and give it to everybody. And so to try to avoid that is, the people doing the study, doing the experiment don't know what group is getting which thing, and we don't know who's being assigned to what. That way they can't, kind of pad the stats, if you want to call it that standpoint, and stuff. So here we have an example where we're going to go through and let me make sure where I'm at in my notes here. Man, I'm flying. That's what happens when you get to fill in the blanks. It starts going quick. But now we get to slow down. So they ask us in this one here is to create an outline to show how to put together a good experiment that meets the principles of design. See you guys. Again, you're going to have to do this for me on our test on Friday. All right, guaranteed there's going to be a question on the free response where you're going to have to do an outline. So here's an example of what you could do. Okay. Many students regularly consume caffeine to help them stay alert. Thus, it seems plausible that taking caffeine might increase an individual's pulse rate. Is this true? That's the question we have. One way to investigate this is to have 20 volunteers measure their pulse rates, drink some cola with caffeine, measure their pulse rates again after 10 minutes, and then calculate the increase in pulse rate. So we're going to go through and try to outline what it would look like. And I'm going to use kind of like a tree diagram or a process mapping process to do it with. And this is acceptable for doing on the AP exam as opposed to having to explain it out in coherent paragraph sentences. Okay, you can use this kind of method, which I think makes it a little bit quicker to do. So the first thing as we look at our design, our outline, we got 20 volunteers. So that's where we're starting with. We got 20 volunteers. We are splitting them up into a group that gets caffeine and then no caffeine. Okay, so we need to, as we look at splitting them up, in this stage right here, we got to talk about how are we getting our random assignment. Random assignment. Using slips of paper. So that's what's happening right here. In this stage, we're doing our random assignments. Maybe I'm going through and saying, okay, I'm going to put the 20 names in a hat on similar sized pieces of paper, and the first 10 names I pull out are going to go to group 1. The next 10 are going to go to group 2 automatically. So somewhere you would define how you're assigning that. So we got group 1 is going to be they're getting our we're going to say that we got caffeine in our soda. And then group 2 would be non-caffeine. No caffeine. And this is what this is going to be our control group. Again, if you choose to do the random assignment by the random number generator, you would go through the same thing, saying I'm gonna assign everybody a number from 1 to 20, and the first 10 numbers selected without repeats will go to group 1. The remaining people will go to group 2. Okay, so you'd have to specify as you do that. I'm gonna try to split that in half there. There we go. Now we're going to measure the pulse rate for both groups. After we give them we put them in the groups, they consume their caffeine, or they consume their sodas. Sorry about that. Consume the sodas. So we measure the pulse. And then now we get to analyze the data. And so that is a simple outline of a good experiment. Now, we would try to make sure that it is definitely single blind so that people don't know which one they're going into. We just know that they're going into group 1 or group 2. They just don't know what's the difference between the two groups. If there was a way to make it double blind to where the people doing the sorting and doing that process had no idea, then that would be great to make it a double blind. But again, this is a typical way on the AP exam, on what we're doing later this week, to kind of show an outline. Yes, there are other ways to do it. You just got to make sure that you specify how are things being split up, how are you doing the random assignment using one of the methods that we learned yesterday. And then we want to talk about here's the first treatment. Then we're measuring the pulse rate, and then we get to analyze the data at the end. Now, here are some specific type of randomized comparative design. We have what's known as a block design. This is an experimental version of a stratified random sample. We break our subjects into 2 or more groups of similar characteristics, like gender or age. It's called a block. We then randomly assign each subject to a block from a block to a treatment. We do this for each block. Blocks act as another form of control. They control the effects of some lurking variables by bringing those variables into the experiment in the forms of the blocks. Like if we're doing the experiment with men and women. Okay, if I want to see how does this thing affect males and affect women, because how a medicine affects a male and a woman is different. Even age part, even the weight of people. And so there's a lot of things, but to start the process of blocking, hey, let's start and break it off by gender first. And then from there we can try to isolate other potential lurking variables if need be. Here is a sample block design. Anne is an avid baker who would like to compare 2 different chocolate chip cookies, recipe A and recipe B. Again, if any of you are, you can always, do this same thing here, and I'll be glad to sample. She recruits 10 volunteer testers at the rate to rate each cookie type on a scale from 1 to 5. She'll make 10 of each type of cookies for a total of 20. Each cookie tray will only hold 10 cookies. So she will use 2 trays and bake them at the same time in the same oven, 1 sheet on the lower rack and 1 sheet on the upper rack. So to try to make it as best as she could, is she said, okay, you know what? I'm going to split it up. There's going to be, 10 cookies on the top rack, and then there's going to be 10 cookies on the bottom rack. And then now we're going to say we got to randomly assign the cookies, because you don't want to put like all the chocolate chips on one rack and then all the sugar cookies on the next rack, because we're not going to know how baking on the different racks is it going to be different for the type of cookie that it is. So what she decided to do was, as we split it up, she's going to randomly assign, type A to one part, half of each type of cookie is going to be on the top rack, and half of each type of cookie is going to be on the bottom rack as they're being assigned onto the tray. And then after that, then the taste tester comes into play. All right, this is the fun job. So, there's an example of a block design. Any of you bake, out of curiosity? No. I like cooking. I like baking, and I notice though when I'm making things, cooking things, that where things are placed in the oven, it cooks it differently and so forth, and it can be frustrating at times as you're trying to cook multiple things in the same oven. So as she's trying to get a true idea of, do you like my cookies? We got to make sure they're cooked evenly, so that process is not going to taint the judging of the taste of the actual cookie itself. So a matched pair design. I will tell you this example, matched pair, pops up quite frequently on the AP exam as you choosing a matched pair as the design, especially with some of our latter topics when we talk about some of our hypothesis testing and other stuff, is where it's based off of a matched pair. So that's definitely one to think about. This is a special case of a block design with 2 options. The first option is that it pairs subjects together based on their similarities. One subject from the pair is randomly assigned to a treatment, and the other subject will receive the other treatment. The second option is the subject receives 2 treatments. The treatments received first would randomly assign for each subject. And we're going to do an example of that here in a minute in class here. I do not have cookies to share, so it's not that. But we're actually going to do an example of this here in a moment. So, and that's what pretty much the rest of class is doing several different of these things that we can actually do hands-on. So now I don't have 32 kids in the class. We only have 9. Okay, we only have 9 kids here. Okay, obviously it'd be great as we look at some of the inferential statistics we're going to talk about in the later chapters. We would love to have a sample of 30, because if we're close to being a sample size of 30 and above, then we are what we call approximately normal. Anything less than 30, sometimes the data, because there's not as much there, has a tendency not to be normal. When displayed, it may look skewed. And so we got to be very careful. And with us only having 9, there is potential for just a couple of the data points in here that could alter some of the numerical summaries that we get. And some may not. So again, we're going to try to do this one live here. We got a class of 9 that we're going to test this theory. Is standing pulse rate different from sitting pulse rate? They are arranged. So basically, you guys are going to arrange in your classroom. I have you just the way that you are. What we're supposed to do is, in alphabetical order, they assign a person a single-digit number from a table of random digits. All subjects assigned with an even number are going to stand first. All subjects assigned with an odd number will sit first. They will be in their assigned position for several minutes, letting their bodies get used to the position. They will count their pulse rate for 1 minute, record the value, then switch positions. again, waiting for the body to get used to that position before taking their pulse. Kai, did you guys do that in clinicals? Yeah. So we're going to do that. Now, we're only going to have 9 here. So now you guys are technically in my grade book assigned odd and an even number because I have 9 kids. And so the first person in the alphabet alphabetically would be the 1, and the last person in the alphabet would be the 9, and then we would go kind of from there. So I think you're 1, you're 2. Thinking about it. No, you're last. You're 9. You're 9. You're 8. You're 2. You're 1. No, you're 1. You're 1. You're 2. You're 3. You're 3. Yeah. Yeah. 8. Yeah. H, and then we go. Let's see, Claire. So you're being what am I? 4. Like 4, 5.
A lot closer than I intended to be. I'm very
7.
sorry.
Yes. Yeah. So. So that's right. It's just there's 1, 2, 3, 4, and then what I said 5, 6, 7, 8, 9. All right. So all right. So you got your number. So while we stall, what do they say here? All the even numbers stand up or the odds? Odds will sit first. So all the evens, go ahead and stand up. If I assigned you an even number, stand up. We got to give it a moment. All right, we got to give it a moment to give you a chance for your pulse rate to kind of adjust to standing up, because when you stand up, sometimes it's an effort, and therefore, like with me, it's a lot of effort. You got to give it a chance to get used to it. Now, do you know how to take your pulse? Does anybody not know how to take their pulse? All right. So you got options of either, I guess, looking at your watch, but I would let's go with this rate of 2 fingers on the side of your wrist. There is one way you could do it. I can feel my pulse right now. Okay. And then the other way is you can go up here. You know, when I get my set team calls, that's where I'm going. So it's wherever you feel it easier. You can feel it right up in here. Okay. Now, that's the one thing you want to protect this thing, because that's the what? Yeah. And if that thing gets damaged, what happens real quick? You bleed out quick. Okay, cutting that little sucker there. So with that in mind, I'm going to shut up here in a minute. I'm going to put a timer up there. We're going to count it for a minute. So I'm going to let the timer go off for a minute. You just count. Once I hit start, you just count, and then record your number. Then I'm going to get all those numbers here in a second. So. So all you're doing is going to count in your head, in your mind, when I get ready to tell you, and I'm going to go stopwatch mode. That'd be easier, okay, than doing the countdown. Okay. So we all okay? All right. Everybody got their fingers on their pulse. When I hit the words START, start counting. Okay. And then we'll go and start. Stop. Record that number.
I got to like 50 and I was like, oh, I got to 49 and I went back to 42 for some reason.
All right. So starting off numerically, what was your number for? Okay, and now you were sitting, right? The odds were sitting. So, okay, what did you have for yours?
Maybe like a rough estimate.
Yeah, I know you lost count. Would you have rough estimate?
Okay, so I was at like 49 when we're at like 30 seconds. So we can go somewhere around like 100. I don't know.
All right, so it was high. So you're already at you had 49 at 30 seconds. So it was running high, wasn't it?
Mine runs high anyways.
Yours run high.
Yeah.
You got an Apple Watch on?
No, I just
Okay.
no.
No, I was just curious.
When I go to the doctor often,
Okay.
I'm always running
Okay.
high.
So we'll go 100. All right, Paula. 79. All right, Andre. 79, and you were sitting. Okay, and Emma Sinclair. Okay, and 74. All right, and Kaida. What? 100, and you were standing, right? Okay, and Alex, right? 90. Okay, and then Jean.
82.
Okay, and then Mackenzie.
82.
Okay, all right. So now my odds, I need you to stand up, and we're going to give you a moment to do it.
I feel like I'm just gonna like get nice something.
So we're just going to pause and just just give you a chance to let it to catch up there. Okay. It's hard.
I run high, but I don't run that high. I'd probably just be dead.
Now, careful when you talk a lot. Sometimes it's, I was doing mine too when we were doing that. I mean, I was getting up there. I think I was 70 something too, 70 something when it went off. Now, again, this is a matched pairs design is when each individual in a way gets both treatments. You're getting the standing up and the sitting down. You're doing both things. And ideally, when you're working with smaller samples, it'd be great to do that. That way, as you look at the difference there. All right. And then we'll give you a chance to do those, and then we'll do the stuff here in a minute. All right. We ready? Begin. Oops, sorry. I meant to say stop. My bad. I was reading the next example. All right. Starting from the top. I'm going to use different color. All right. What do we have?
Kind of like 105.
Okay. Paula? 52? 82. Okay. Sorry, air conditioner. Number 3? 99. All right. Number 4? You say 76 or 72? 77. Oh, identical. All right. Ava. Okay. Kaida. Would you say 90? Okay. All right. And then Alex. 93. And then Jean. 71. And then Mackenzie. 85. All right. All right. So now go ahead and have a seat there. Thank you for participating. And then now we go through and we're going to say, all right, let's find the difference. Standing minus sitting. So that would be a positive 5. That would be a negative 3. A positive 20. 0. And then we would have a positive 12. A positive 10, a positive 3, a positive 11, and a positive 3. Okay. Now they asked us to do a dot plot. So, and again, here's the challenge with only 9 subjects. All right, so let's see. We had 3 happened. Well, whoop, got a negative 3. Whoops. 1, 2, 3. Negative 3. Negative 3. Then we have 1, 2, 3. 2 of those. We have a 5. We have a 10, 5, 6, 7, 8, 9, 10, 11, 12. And a 20. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So, now, as we kind of look at our summary again, this is the difference in pulse rate as we label, and we did standing minus sitting. As if this is what we're doing for an example on the AP exam for response, you need to make sure that you label that dot plot. What is it? How did we get those numbers? We did the standing minus the sitting pulse rate. Anytime we're asked to kind of analyze or describe what we see in a graph, we should be thinking about the SOX. I wrote that acronym on the test that I was giving back to you all. What does the spread look, what does the shape look like? That's the first one. So as we look at the shape, the challenge with the lack of numbers, it's hard to see, okay, is it skewed? There is a greater frequency of data closer to 0. So we could say this is skewed right. We could. It wouldn't be bad to say in a way it's almost uniform, because you had things being listed once or one thing happened twice. Okay, drawing the little the skew, drawing the picture of the shape kind of makes it tough because we just don't have a lot. But there is a lot of data here. When we look at the data on the left side here, there are more occurrences on the left side there to where this would, we could classify this as being kind of skewed right. Granted, that's a real, distortion of the skewness there, but we could say that. We could, if we wanted to, find the mean. We could find the median. Since it's skewed, we'd go with more with the median of describe it. Is there an outlier? We would, that's what the O is. We want to say that maybe a potential outlier. At 20. All right, that's a potential outlier based on this data. What would I do to check to see if it was numerically an outlier? What could I do? Did we forget that fast? Yeah, the 1.5 times IQR rule. Okay, that's what I should do. I should go through, type in real quickly in a table 5, -3, 20, 0, 12, 10, 3, 11, and 3, and then tell it to do a 1 var stat, figure out what Q1 and Q3 are. And then, then I could go through and figure out what the IQR is, multiply it by 1.5, add it to whatever Q3 is, and then see is 20, is it an outlier? That's what I should do, okay? The center for the C, it kind of looks like the center's probably around 3. The 3, there is an odd number, so 5 is the median. So when we think about it, the median is 5. The median is 5. The mean technically is going to be a lot bigger. Okay, the mean, if this is skewed, the 20 is going to make the mean be a lot bigger than what it should be. The mean is going to probably be somewhere, I would assume around 7 to 9 is what I'm assuming for the mean. Might be bigger than that, just because of having the 20 there, having the 12 and the 11, having these 4 big numbers there. And then our spread. We would say that there's a range of 23. We went from -3 all the way up to +20. So there's a range of 23. Now, statistically significant, and we're going to see that term come up quite often in our course. Is it statistically significant? It's statistically significant when an observed effect is so large that it can really rarely occur by chance. Mr. Stevens forgot to fill in that one. We use probability to determine if our results are statistically significant. For example, if there is only a 1% chance of getting the result from the experiment that we got, we call that result statistically significant. That we did not get these results by chance and that these are true results. Okay, so to me, there's no set cutoff, but once we start seeing, hey, what's the percent chance of this thing occurring? And if it's 15, 20, 30%, well, that's not, then we see that it's not statistically significant, because, hey, it happened quite frequently. So, so here is an example. I haven't tried this one yet with the class. Is talking on a cell phone while driving more distracted than talking to a passenger? Are these results statistically significant? To find out, let's see what would happen just by chance if we randomly assign the 48 people in this experiment to the 2 groups many times, assuming the treatment received doesn't affect whether a driver stops at the rest area. All right, so what do we need? We need 48 cards to represent the drivers in the study. Like the original experiment, we will use 33 cards to represent drivers who stop and 15 cards to represent those who did not stop. Shuffle and deal 2 piles of 24 cards. The first pile represents the cell phone group, and the second pile represents the passenger group. The shuffling reflects our assumption that the outcome for each subject is not affected by the treatment. So, record the number of drivers who failed to stop at the rest at each. All right. So, we're going to pause. We're going to turn off the video. I'm going to grab some cards and we're going to try this. See how easy this is and how it is not. So, let me go.